So, as uh, no one no one has joined yet, so I just start my discussion over here. So today I'm going to discuss about the topic of 8 weeks, eighth weeks, eighth week. Sorry, and the topic for this discussion is abstract vector space. So we are going to, so here is basically I'm going to discuss about the polynomial vector space and a little bit on inner product vector space, inner product space. Okay, so let's start. So we have already studied the vector space. Okay, so in that vector space, we have studied that there are certain rules, certain axiom that has to follow. The space is said to be a vector space if there are certain space is said to be a vector space if there are certain axioms that the element of that space can follow that certain axiom. If the all the elements can follow those actions, then we call that space is a vector space. So we have already discussed about what are those things, and we are going to discuss in detail on that. So let me write down all the actions. Just a minute. So let V is a vector space which is defined by two operations. One is vector addition and scalar multiplication. So this is dot for the multiplication. Okay, is said to be a vector space. We just first recall all those actions, then we move to the Poisson space. If the elements of that space follow the following 8 axioms. Okay, so what is the first axiom? So the first axiom, as we know, is basically commutative property. So now let x and y belongs to vector space. If x and y belong to vector space, then the rule said x plus y equals to y plus x. That means that commutative property has to be followed, right? What is the second property? Second property is associativity. So associativity says that x, y, and z all belong to vector space. Then x plus y plus z, I should write it over here. Then x plus, first we add x plus y, and then we add z to that addition is equals to x plus y plus z. Okay, this is the second. So the first rule is, uh, let me write it over here. So this is called commutativity. Okay, and this one called associativity. Then the third, what is the third? Third says there must exist a zero vector. Okay, so let's say that there must exist a, so there must exist a zero vector such that x plus 0 equals to x. So this is vector, that's why I just uh, make it a bit darker for all x belongs to z, right? So this is called, so this one is called, this property is called additive identity. additive identity. Okay, I'm sorry. Now the fourth one. So there must exist a negative vector. So I'm just using a sign. There must exist a negative vector minus x. Okay, such that if we add x with minus x, we will get a zero vector. Okay, so there must exist, if there exists, that means it says that if there exists a vector x in that space, so there must exist a vector minus x in that space, so that if we add these two vector, we get a zero vector. So this is basically, say, this property or this axiom is called additive inverse. Okay, now move to the fifth property. Fifth property is there exists a scalar. Okay, so fifth property is now we are done, basically done with the additive properties. Now move to the multiplicative properties. The first multiplicative property is if we if let's say x and y belongs to V, which is a space, vector space, and there exists, let's say, alpha, which belongs to some real number. Okay, then the axiom says alpha times x plus y should be equals to alpha times x plus alpha times y, right? So this property is basically called distributivity. Okay, so this property is so here basically we are talking about the scalar multiplication, right? Scalar multiplication. So here I have used two terms, right? A vector space with the two operations over there. Where one is the addition, vector addition, and there is a scalar multiplication. So here I'm talking about this scalar multiplication property. Because vector addition already I have talked about. Okay. Similarly, the sixth one is basically the same. For x belongs to V and alpha comma beta belongs to some real number, then alpha plus beta into scalar multiplied with x is equals to basically alpha times x plus beta times x. So this is also called distributive property. Okay. Then the seventh rule is said like for x belongs to V and alpha comma beta belongs to R, then alpha beta, we multiplied alpha beta and then we do the scalar multiplication with the vector is similar to alpha times beta into x. Okay, so this is same. Okay, and the eighth, this is basically mixed associativity. This is also an associativity in multiplication rule. Basically, this is the mixed associativity, and the eighth axiom is there exists a scalar for 1. Okay, there exists a scalar 1 such that 1 times x equals to x, or all x belongs to V. This property is called here I'm since you have joined just now, so I have started my discussion. So here I'm going to discuss about the topic of eighth week. Okay, so I just prepone this whole thing, prepone this whole discussion session. So today I'm going to discuss about the abstract algebra, which is mainly focused or which will be mainly focused on the polynomial vector space and a little bit on inner product space. Okay, so here I have just start with a preliminary because we have already studied the vector space. So we know that a space is said to be a vector space if the elements of that vector space follows certain rules, certain axioms, right? So I have just written down all those axioms. So here basically I'm saying that V is said to be V. So each vector space. So first of all, when we denote a vector space, so obviously we denote the operation over there. So what kind of operation can be done between the elements in that space? Okay, so we can't do any kind of random operation, so there has to be a certain operation. So that's why I have mentioned over here that V is the vector space. Okay, and it has a two operation. One is a vector addition, this one is a vector addition, and another is a scalar multiplication. Okay, so so we sometime in book you can see that with this notation they denote the vector spaces. So this vector space is said to be this space is basically said to be a vector space if the elements of that space follow the eighth, total eight axioms. So what are the axioms? What are the rules? So first rule says that if x and y belongs to V, then this commutative property should satisfy. That means x plus y is equal to y plus x. The second one said that if there are x, y, and z in V, then this associativity property, that is, first we add the x plus y, and then with this addition we add z, or first we take the addition of y plus z and we do the addition of x with the resultant addition. Then both are equal. We'll give a equal response. Okay, the third one is additive identity. Identity means there must exist a zero vector. If we add any vector of that vector space with zero vector, we return to that. We get the zero vector. We get the vector itself. Then the additive inverse. Additive inverse means if there exists x, there must exist minus x. So that if we add these two vector, we get a zero vector. This is additive inverse property. The fifth one is distributivity. So here we are talking about the scalar multiplication. So right now, till now we have talked about the vector addition. Now we have talked about scalar multiplication. So I'm saying that there are alpha is a scalar term, okay, which belongs to this real number, and x, y are the two vectors which belongs to this vector space V. Okay. Now if we multiply alpha with these two with the addition of these vectors, then this is similar to the multiply each vector with the scalar and then take the addition. Okay. The sixth one is similar, is basically if we take a two scalar from the field which is denoted by a real number, then alpha plus beta multiplied with x is similar to alpha into x plus beta into x. This property is also distributive property. This property, this is mixed associativity. So where it says that first we multiply these two scalar alpha and beta, and then we multiply this scalar, the resultant scalar, with the vector. This is similar to alpha into beta into x. Okay, and the last one is basically called a normalization. So that means there must exist, obviously there must exist a scalar term 1, and so that if we multiply a scalar with a vector, we get the same vector. Okay, so these are the eight axioms that each element of any space has to follow If they follow all these rules, then it is said that that space is a vector space. Okay. So now we have already discussed about a vector space. Now we are talking about a polynomial vector space. Polynomial vector space means, so if, okay, okay. So polynomial vector space is basically okay, I'm sorry. So a polynomial vector space is basically, it's a, let's say P. So P is said to be Pn, let's say Pn is said to be a vector space, okay, of degree n. So degree n means, there, when I'm talking about polynomial, so there is not a single element I'm talking about. It's basically a function is basically a function of degree 1, 2, 3, 4, 5, 6, whatever, up to n, or maybe more than n. Okay. So here I'm just confine this space to a n degree. Okay, confine means like the maximum degree or at that space Pn, the maximum degree at that space Pn is can cannot be greater than n basically. Okay, so is said to be a vector space of degree n if it follows the above axiom, right? If it follows the above axiom, so here we are not going to discuss about anything like basis. We are not doing all those things. I mean, we are not going to talk about the basis or all those, because we have already talked about what is basis and what is the linear independency, what is the span, everything we have talked about, right? So there is nothing to talk about all those things. So the standard basis, basically, standard basis, normal. If we say a standard basis for a vector space in 3 dimension, for a vector space in, first of all, okay, in 3 dimension, what is the standard basis? What would be the standard basis in 3 dimension? If we look, we all know that basis is not a fixed one, right? Basis could be anything, but just to remember, there has to be all the vectors in the basis space. There has to be linearly independent with each other, and there has to be a right number of vectors, number of vectors should be in there. Okay, the exact number of vectors should be in there. So obviously, the in 3 dimension, the basis should be basis for a vector space in 3 dimension. Let's say I'm calling it a B1. So what are the bases? Obviously, the standard basis that we consider 1, 0, 0, 0, 1, 0, and 0, 0, 1, right? We basically studied about all those things. Like this is the basis for standard basis for vector space. Okay, but this is not a basis, is not a unique one. Okay, that means we can generate any vector in the 3D space. We can generate any vector by using this basis vector. We can generate any vector in 3D space by using this basis vector. Okay, so now similarly, if we say P2, P2 is a polynomial vector space of degree 2. Okay, so what would be the basis for this P2? So the standard basis for P2, I'm calling it V suffix P2. Okay, is basically 1 x and x square. So maximum degree at that polynomial vector space, I have said that maximum degree at that polynomial vector space is 2. Okay, so that means maximum degree of x could be 2, right? So this is basically the standard basis for P2, where the polynomial's maximum degree is 2. Okay, polynomial degree is 2. Now, what is the dimension of this space? Dimension. What is the dimension of this P2? So dimension of P2, what could be the dimension of P2? So we have studied that the number of vectors or number of elements in the basis basically equals to the dimension of that space. So what are the elements? What are the number of how many elements are there in the basis? There are 3 elements, right? So dimension of P2 is 3. Okay. Similarly, if we call Pn is a n degree polynomial vector space, right? So the standard basis for Pn, what will be the standard basis for Pn? So similarly, it would be 1 x square up to x to the power n, right? So what would be the dimension of Pn? So there are n element, n plus 1 element. So it would be n plus 1. Dimension of P1 is n plus 1. So here I start with an example. I hope you have understand what I am talking about. Okay. So the first example, the question is P3 is a vector space of degree 3. Okay. Now consider there exists a polynomial, say p small p of x is equal to a x cube. This is the polynomial that exists over there. Okay. So a belongs to real number. So a belongs to some real number. Okay. Now the question is small px is a subspace of P3. Okay. So the question in a question we have given the first thing what we have given, it says that P3 is a vector space. So it has already said that P3 is a vector space of degree 3. That means in capital P3
in the space of capital P3 there exist the polynomials whose degree there exist all the polynomials, okay, whose degree is 3. Like it could be 1 plus x square plus x cube, it could be x cube, it could be twice x cube, it could be, let's say, 1 minus x cube or 1 minus x square plus x cube. So all these polynomials whose degree, the highest degree is 3, all those polynomials are lie in P3. Okay, and it said that it is a vector space. Now from that vector space we have here the we have consider a polynomials, we have considered a set of polynomials which looks like something ax cube. Okay, so from that vector space, from that P3, we extract polynomials which looks like ax cube. Okay, so those polynomials we extract where a is basically the elements of real number. Now the question says that this set of polynomials, this px, small px, is a subspace of P3. Is it? So we know that subspace of a vector space is basically itself is a vector. The subspace of a vector space is itself a vector space. So that means the subspace has to follow all the eight axioms. All the 8 axioms has to follow, right? So here we are not going into that all those 8 axioms. We have just check that whether there exists a zero vector. Is there exists a zero vector? We have to check that vector addition satisfied, and we are checking that scalar multiplication satisfied or not, and then we are basically done with that. Because if these things can be satisfied, then all those distributed property and those can be satisfied. Okay, so the first checking should be existence of zero vector. Okay, now here we have said that, so the polynomial is px equals to a x cube, where a belongs to R. Since a belongs to R, that means a, so since a belongs to R, this implies a could be equals to 0. Now this, if a could be equals to 0, that means this implies my px is 0, right? My px is 0. So that means zero vector exists. That means what zero vector says? This is basically additive identity. We have to check the additive identity. Now, if we collect any px, now let qx or any other px. Now let consider, sorry, consider this px. Okay, consider any px from this set of px. We consider any px from the set of px. So a is real number, right? So we can consider any px from the set of px. Now consider any px from the set of px. So px plus 0, we get px. That means my first condition satisfied, that there exists a zero vector which can do the additive identity, which implies that additive identity exists in that space. Now second thing is consider any two real number a1, a2 are the two real number that belongs to R. Okay, because A is R, so a1, a2 that belongs to R. So we have, let's say p1x, we call this p1x equals to a1 x cube, and p2x equals to a2 x cube, right? So if we add this p1x plus p2x, what we get? A1 x cube plus a2 x cube. What it says is a1 plus a2 multiplied with x cube, right? A1 plus a2 multiplied with x cube. Okay, so this a1, a2, the addition of real number exists in real number, because addition of real number can't be any complex. Addition of real number is x. So this is another real number. So this implies that p1x plus p2x belongs to this set of x cube. Why? Because a1 plus a2 belongs to real number, right? So addition property satisfied. Now we have to check the third one is multiplicative property. Now consider C belongs to some real number. Okay. Now we are going to multiply C into Px. Scalar multiplication we are doing. So what is Px? C into Ax cube, right? C into Ax cube. So if we use that mix associativity property, so what it means? C into A multiplied with x cube. So C into A, Ca belongs to real number. This implies C of Px belongs to this Ax cube set, right? So this satisfies that Px, which is Ax cube, is a subspace of P3. Okay, so I hope you have understand. Now move to the next example. So the next example says, consider a subspace of all polynomials of degree n with root at x equals to 2, such that U is basically a set of Px belongs to this Pn, such that P2 equals to 0. The question says that find the basis of U. Okay. So uh, if you have any queries regarding today's topic, because this is basically a preponed class that uh, I am basically discussing over here, because this should be the topic of the next week. Okay, this should not be the topic of the today's weekend, but here I just prepone this class. So you have any queries, you can ask in the forum,
so that I can answer over there. Okay. So let's move to the example. So it says that we have considered first it says that consider a subspace of all polynomials of degree n. So here Pn subspace I should write over here because otherwise Pn should be undefined subspace Pn of. So I'm saying that Pn is basically a subspace which consider all the polynomials of degree n. Okay. And also it says that polynomials of degree n with roots at x equals to 2. That means those polynomials who are in Pn is basically who are in Pn is basically sorry, my mistake. This should be off because Pn is a polynomial. Uh, I should write over here. Pn is a space of or vector space of all polynomials of degree n, right? So here, Pn here is a polynomial of degree n. Now, the question says we have to consider all those polynomial of degree n whose roots are at x equals to 2. That means say the U is that subspace where all the px existed, which all the px which are belongs to Pn, all the px existed such that roots at x equals to 2 exist. That means P2 equals to 0. Okay, P2 equals to 0. Now we have to find out the basis of U. Okay. So first of all, the subspace that they have defined is all the Px from Pn such that P2 equals to 0. Okay, this is the subspace that is given to us. Okay. Now Pn is a set of or is a space of all polynomials of degree n. So Pn consists all the polynomials of degree n. There is no extra properties or there. No, the extra properties that exist in U. Okay, the extra properties say that those n degree polynomials should have roots at 2. Okay, but Pn says it is a polynomial. It is a space of polynomials of degree n. Okay, so for n degree polynomial, for the space of n degree polynomial, what is the standard basis? So standard basis for n degree polynomial is this. Okay. So therefore, standard basis for Pn is 1 x square up to x to the power n, right? Now we have to find out the basis for this U, right? So we know that now given is Px belongs to this U, right? And Px has roots at x equals to 2.
So what what does this line mean? This line, what does this line mean? This line means, this means all the polynomials Px belongs to U must be divisible by x equals x minus 2, right? This means all the polynomials Px which belongs to U must be divisible by x minus 2, because at x equals to 2 there exists a root. Those polynomials at x equals to 2 has roots. Okay, so that means they all are divisible by x minus 2. So therefore, any polynomials in U can be expressed as this: Px equals to x minus 2 into some polynomial Qx, right? We can express all those Px which are belongs to U can be expressed like this, right? Is it okay to all of you? That means Px itself is a n degree polynomial. So what it what it signifies, what this signifies, Px is n degree polynomial, right? Now this is a polynomial of degree 1. This is 1 degree polynomial. So what should be the degree of Qx? So Qx must be n minus 1 degree polynomial, right? This should be the thing, because 1 multiplied should be the if 1 degree polynomial multiplied with n minus 1 degree polynomial, we get n degree polynomial, right? Up to this point, everything is clear to all of you, right? So that means, so this means Qx belongs to some Pn minus 1, right? Because here I've said that Pn is a space of all the polynomials of degree n. So we can write that Pn minus 1 is a set of all the polynomials of degree n minus 1. So that means Qx belongs to Pn minus 1. Now what will be the standard basis for Pn minus 1? So the standard basis for Pn minus 1 is sorry 1 x square up to x to the power n minus 1. Maximum degree of that of the polynomial of that space Pn minus 1 should be n minus 1. So this is the standard basis. Okay. Now we can represent, so this is basically the standard basis, right? So that means we can represent Qx using the standard basis. So if we multiply and those that Qx which are represented by the standard basis with x minus 2, we get Px. Is it okay for you? We have a standard basis. We know that basis is not unique, but standard basis, using that standard basis, we can define any vectors of that space, obviously. So this is basically the standard basis. If this is the standard basis of Pn minus 1, that means we can represent this Qx polynomial using the standard basis. And now if we multiply this Qx, which is already represented by a standard basis this, with term x minus 2, we get px, right? This is obvious. So that means, so what would be the basis? Because already qx is represented by the standard basis. And now I'm multiplying x minus 2 with the qx, we get px. Px exists in u. So what would be the basis for u? So the basis of the space u should be x minus 2, x minus 2 multiplied with x minus 2 multiplied with x square up to x minus 2 multiplied with xn minus 1. Okay. Is it understandable? So, that means the basis of u is this. But this is not a unique basis. There could be any basis, because if you choose any other basis of Pn minus 1, then we can represent the basis of u based on that basis. So basis is not unique, but the basis should be independent, and the number of basis vector in that basis space should be exact. So since this is the standard basis of Pn minus 1, so they are independent of each other for sure. And now they are multiplied by just an element, just a polynomial, x minus 2. Each independent vector multiplied with a polynomial x minus 2. So definitely the resultant vector are also independent. So that means this could be a basis. Okay. So linear independency satisfied. And then now you have to check the number of the degree of the polynomial is n or not, because what we have said that px is n degree polynomial and px belongs to u. So the basis should exist n degree polynomials, right? So obviously x multiplied with xn minus 1, we get x to the power n. So degree is also satisfied, right? So this is basically the basis of u. Now move to next example. As you have, none of you have joined this class today. So the next question is something like that. So here I'm going to, we are basically maximum portion, we are basically discuss about today discuss about the polynomials, polynomial vector space. Okay. So P3 be the set of polynomials of at most degree 3. Okay. So P3 is said to be a set of polynomials where at most degree of the polynomials is 3. The at most degree of polynomial means the any polynomial cannot exceed, the degree of the polynomials cannot exceed 3. So in P3 there exists, let's say 1. There could be exist only a polynomial x square. If there could be exist polynomial 1 plus x square, could be exist a polynomial 1 plus x square plus x cube. But the degree of the polynomial can't exceed 3. Okay. So P3 be the set of polynomials of at most degree 3. Now consider the following
ordered basis of P3. Okay, so what is the ordered basis? So BP3 is, say, that 1 plus x, 1 plus x square, x minus x square plus 2x cube, and 1 minus x square. So this is the ordered basis of P3. Now the question says, write the coordinate vector for the polynomials So you have already studied the coordinate vector in vector space discussion, right? So I do not need to discuss about what is the coordinate vector and all. Polynomial f of x equals to minus 3 plus 2x cube. So this is the polynomial f of x. Now it says that we have to find out the coordinate vector of this polynomial in terms of this basis vector bp3. Okay. So since P3 is the polynomial of at most degree, the standard basis could be 1x, x square, and x cube, right? Now we have to represent this polynomial fx. We have to represent this polynomial fx in terms of bp3. So the constant term that is multiplied with each basis is basically the coordinate vector, right? So we have to find out the constant term. So that means we can say that alpha, we can represent any polynomial inside P3. So obviously this is also the polynomial of P3. This fx is also a polynomial that exists in P3 because polynomial is said to be P3 is said to be the point state of polynomials at most degree 3. So we can represent fx using this basis vector that we have given, right? So we can write that alpha not 1 plus x plus alpha 1, 1 plus x square plus alpha 2, 1, sorry, it's x minus x square plus 2x cube, and alpha 3, that is 1 minus x square. This could be minus 3 plus 2x cube, right? Very simple. Because these are basis vector and we can represent the vector, any vectors from that space using this basis vector. Okay. Now, the standard basis, now the standard basis of P3, what is the standard basis? I'm calling it as S. The standard basis of P3 is 1x, x square, and x cube. Now, using this standard basis, we can represent this whole basis vector as well, right? So using this standard basis, we can represent this vector, we can represent this, we can represent that one, we can represent that one, right? Using this standard basis. Very simple. So I'm going to represent 1 plus x using this standard basis. So what should be the coordinate vector? What should be the coordinate vector? 1 plus x. It is 1, 1, 0, 0.
That means alpha naught multiplies 1 plus alpha 1 multiplies x plus alpha 2 multiplies x square plus alpha 3 multiplies x cube. This should be equals to 1 plus x. So if we put alpha 2 and alpha 3 0, we get 1 plus x, right? And put alpha naught and alpha 1 1 1, then we get. So this is basically the coordinate vector, right? Now we can represent 1 plus x square using this basis vector, right? Because this is also, I'm just representing the ordered basis vector in terms of standard basis vector. And from there, I'm just computing the coordinate. Okay, 1 0 1 0. Now the next one is x minus x square plus 2x cube, right? And we can represent it in a standard basis vector manner. So it is 0, 1, minus 1, and 2. And the last one is 1 minus x square. It's a 1, minus 1, minus 1, and finally 0, right? And also minus 3 plus 2x cube, we can also represent using the standard basis. So that means minus 3 0 0 2. So this is the coordinate vector. We can also represent fx in terms of standard basis vector, right? Now we have to represent fx in terms of ordered basis vector, and from there we get the coordinates. So that means in this equation, just like I used the previous logic, here I have represent qx. Here I have represent qx by using a standard basis, and then multiplied with x minus 2, we get px, and that basically considered as a basis of u. I'm using the same logic over here, right? So alpha naught multiplied with 1 1 0 0 plus alpha 1 multiplied with 1 0 1 0 plus alpha 2 multiplied with 0 1 minus 1 2 and plus alpha 3 multiplied with 1 minus 1 minus 1 0. This is equals to the coordinate vector, that is 3 0 0 2. So we can write it in this matrix vector format. So 1 1 0 0 1 0 1 0 0 1 minus 1 2 and 1 minus 1 minus 1 0. Alpha naught, alpha 1, alpha 2, alpha 3. This is equals to minus 3 0 0 2. Right? Okay, get it? So now how we find out this alpha naught to alpha n? We just augment this thing and check and do the Gauss elimination method. So I'm doing the same procedure over here. First, we just augment A with B, and then we do the row operation. So first row operation is I need to do this term to 0, Gauss elimination method. Just we have studied in first two discussion. So R2 is basically R2 minus R1. Okay. Right.
So this is 1, 1, 0, 1. This is minus 3. So R2 minus R1, this is 0. R2 minus R1, this is minus 1. This is 1. This is minus 2. And this is 3. So 0, 1, minus 1, minus 1, 0, and 0, 0, 2, 0. I'm not using that line. Okay. So now we change R3 and how? R3 plus R1, 1, 1, 0, 1, minus 3, 0, minus 1, 1, minus 2, 3. Either you can do only reduce echelon form or you can do row reduce echelon form. I mean, or either you can do the row echelon form or you can do the row reduce echelon form. Okay, so 0, 0, 0, minus 3, and this is basically 3. Yeah, and then 0, 0, 2, 0, 2. So I'm just doing the row echelon form, nothing much. Now exchange R3 and R4. Okay, so if we exchange R3 and R4, what we get? It's 1, 1, 0, 1, minus 3, 0, minus 1, 1, minus 2, 3, 0, 0, 2, 0, 2, and 0, 0, 0, minus 3, 3. So now it's become row echelon form. Okay, so from here, what we get is we get alpha 3. That is from last row, we get alpha 3 equals to minus 1. Right? Alpha 3 equals to minus 1. Now, and from the second last equation, alpha 2, what we get? Alpha 2 equals to 1. Okay, now put this two value in the previous equation, where is it says minus alpha 2 plus alpha 3 minus 2, sorry, minus, my mistake, minus alpha 1 plus alpha 2 minus 2 alpha 3 is equals to 3. Now from here, put the value of alpha 3 and alpha 2, you will get alpha 1, and alpha 1 equals alpha 1 equals to, you will get sorry, 0. Excuse me. And from the first equation, alpha naught plus alpha 1 plus alpha 3 equals to minus 3. So here put the value of alpha 1 and alpha 3, you will get alpha naught, and which is basically alpha naught equals to minus 2. So the coordinate vector alpha naught, alpha 1, alpha 2, alpha 3, this is basically equals to minus 2, 0, 1, minus 1. Right? So if we now if we put the minus 2 into 1 plus x plus 0 into 1 plus x square plus 1 into x minus x square plus 2x cube plus minus 1 into 1 minus x square. So what we get? Minus 2 minus twice x plus x minus x square plus twice x cube minus 1 plus x cube. Sorry, this is not cube, this is square. So what we get? This cancel out, this cancel out, and what we get? Minus 3 plus 2x cube, right? So which is basically nothing but fx. Now we represent fx in terms of the ordered basis vector, right? So therefore, the coordinate, the what the question? The coordinate vector
for the polynomial f of x, which is equals to minus 3 plus twice x cube in terms of dp3 is alpha naught, alpha 1, alpha 2, alpha 3. This is equals to minus 2, 0, 1, minus 1. So, so you have the answer. Okay. So I think it's the question is clear to you, right? Clear to all of you, I hope. Now move to the next example. So the question says, let C 0, comma 3 be the vector space. So you have already seen in the lecture video that the continuous function, the set of continuous function between an interval is also a vector space. So this is basically C defines the continuous function, set of continuous function between interval 0 to 3. Okay, is a vector space of real function on interval so let P3 denote the set of real polynomials of degree 3, degree 3 or less. That means at most degree could be 3. When below degree 3 polynomials can exist in P3. Okay. Now consider a mapping. What is the mapping? P, which takes the element from C03 and map to P3. Okay, so between these two space, there is a mapping called T. And what is the function that mapping is looks like? It looks like T of f of x is equals to some f naught plus f1 x plus f2 x square plus f3 x cube. So the question is now check whether the mapping P is a linear transformation or not. Okay. So you have to check that mapping, whatever the mapping is happening, is a linear transformation or not. So we have studied the linear transformation, right? So there is no need to discuss everything about linear transformation. So what linear transformation says? So linear transformation says, so what linear transformation says? So linear transformation says, so if T is a linear mapping, okay, to I mean, if V and W are the vectors of some vector space, let's say V vectors, some vector space V, and T is a linear mapping, then this thing should happen, right? And if there exists a constant which multiplied with V, then obviously these things should happen. If these two rules happen, that means mapping is linear. That means the transformation is linear. Okay, now we have to check that this is this, because we have already given the mapping, like what would be the structure of the mapping. We have already given the structure of the mapping. We have to check that whether this structure of the mapping follows the superposition theorem or not. Okay, the linearity, theorem of linearity or not, or just you can say T of, let's say, CV plus DW, where C and D are the scalars multiplication, V and W are the vectors. So V, W, let's say, belongs to capital V, are vectors, and T, D belongs to, let's say, some real number. So this could be C into TV plus D into TW. If this happens, then it's a linear mapping. Okay. Now we have to check for our case, this T is a linear mapping or not. Okay. So let's say F and G both belong to this C03. Okay. So now we have to check that T F plus G of X. That means according to the transformation, this is F plus G of 0 plus F plus G of 1 into X plus F plus G of 2 into X square plus F plus G 3 into X cube. So which means that F of 0, we can accumulate the F term together and then G term together. Okay. So F plus 0 from here. So from here F plus 0, from here F1, F0 from here F1 into X, from here F2 into X square, and F3 into X cube. I'm just collecting. So F1 X plus F2 X square plus F3 X cube. And now the G terms exist. So because this is addition, so what happens is same G of 0, G of 1x plus G of 2x square plus G of 3x cube. So this means that T of f of x plus T of g of x. That means, sorry. So T of f plus g of x equals to T of f of x plus T of g of x, right? So that means first linear property satisfied. This property satisfied. Okay, now I have to check this one. If this property is also satisfied, then this is transformation is linear. Okay, then check. The second one is T of some scalar C f into x. This is basically C into f naught x plus C into f1 x
plus, sorry, again I did the wrong thing. So C of F naught plus C multiplied F1 x plus C multiplied F2 x square plus C multiplied F3 x cube. So what we get? Take common C, F naught, F1 x, F2 x square, F3 x cube. So that means this is T of x. So therefore, T is a linear transformation. Right? It's clear to everyone, I hope. Okay. We do one couple of questions from polynomial, and we'll shortly discuss on inner product space, and we will stop there. Okay. So example, so we have the next example is, so let L is a mapping or transformation from P3 to R3. Okay, it takes the elements from the polynomials and it maps to the three-dimensional real plane. Okay, and also said it is a linear transformation. See the linear transformation defined by following: L a t cube plus b t square plus c t plus d equals to, this is some sort of mapping. This looks like a minus b plus c, d plus 2b minus 2c, and b minus c. This is some sort of mapping is look like. So the first, so the question says that okay, just a minute. Yeah. So the question says that find the basis for the null space of L. So whatever the L is, we have to
The question says that you have to find the basis of the null space of L. Not L, you have to find the basis of null space of L. Okay. So what is the null space of L? So all the polynomials in of P3 looks like this, which takes the transformation L and it maps to this format. Okay. So now the question says find the basis for the null space of L. Okay. So null space of L means what? So that means where L multiplied with any polynomials, it gives a 0. That means that is the null space, right? What is the when if we say normally if null space of matrix A, so what is the null space of matrix A? It is basically the solution of Ax equals to 0. We have to find out all those x which multiplied with A and gives a 0. So that means the null space of what is the null space of L? Null space of L would be all the polynomials which takes the transformation L should plot to the 0. That means all these terms should be 0, right? So that means what it says? It says that the null space, sometimes it's called also called kernel. Okay, kernel, Kernel, kernel. The null space of L is basically all the polynomials is a t cube plus b t square plus ct, because this is the polynomials, right? So all the polynomials with these three terms to 0, with a minus b plus c equals to 0, then d plus 2b minus 2c equals to 0, and then finally b minus c equals to 0, right? So that means from here what we get, so this is let's say equation 1, this is let's say equation 2, and this is let's say equation 3. So from equation 3 what we get, b equals to c. Now put this value on equation 1 and 2, we get what we get, a equals to 0 and d equals to 0, right? So this is the thing that we get. So that means polynomials in the null space of L, what would be the structure of the polynomials? So the polynomials in the null space of L of the form of, what is the polynomials? So polynomials, what are the polynomials? Pt is basically, because there is no a, no d, right? And the polynomials is looks like a t cube plus b t square plus c t plus d. So a and d both are 0. So the polynomials are in the form of, let's say, bt square plus bt, right? So this is the polynomials. These are the basically the polynomials of the null space of L, right? Like we are basically trying to find out here all the polynomials, right? And we're trying to find out the basis, all the polynomials which gives a zero values or which gives a zero vector if we do the linear transformation L on those polynomials. So that means the polynomial structure is ATQ plus BT square plus CT plus D, right? Now we need to find out all those polynomials which, if we apply, if we do the linear transformation on those polynomials, we get a zero vector, right? So this is the structure of the polynomials. So therefore, the basis of null space of L is, as I'm calling it BL, is, what will be the basis? It's T square and T, or rather T and T square. This would be the basis. No, sorry, this couldn't be the basis. It's hello, Shabik. Are you the student of this course, Basic Linear Algebra?
Yes, sir.
So you have joined very late because I started this course from 3 p.m. Okay, so I have almost completed the course. I mean, almost completed the topic. Actually, today this is the course of 8th week. Okay, so I just preponed this course, and I think you have all. I mean, you have get the announcement because I have already mentioned it, and you have already get the announcement that the 15th March, the course should be uh, uh, held on 15th March, but due to some problem, I just preponed this course. Okay, 9th March. So today I have discussed about abstract vector space. Okay, mostly the polynomial space. Okay, so because we have already studied the vector space, so that was basically on Rn dimension. That was basically real numbers. We have seen that there are elements of that space are basically the numbers. Okay. Now here we have basically talked about the polynomials. Elements of the space are basically the polynomials. Instead of numbers, there are polynomials. Like 1 is also a polynomial. X, yeah, 1 plus x or 1 plus x square, blah blah blah. So we are basically here talking about the polynomials vector space. Uh, so here what I have discussed so far, I'm just giving you a little recap because since you have joined, so just listen, and after that, already I will post this video, post this YouTube link, and also you will get this note. You can check it over there. So I'm not going into very detail of this. I'm just giving a little recap of this. So abstract, basically, the we have already studied that vector space is a space which has a two methods, that is the addition, vector addition and scalar multiplication, and it has to follow these 8 rules. This also we have studied in previous discussion, that is commutativity, associativity, additive identity, additive inverse, distributivity, normalization. This one is mixed associativity, and this is also distributivity. So now here we talked about mainly on polynomial vector space. So Pn is said to be a vector space if it has said to be a vector space of degree n if it follows this all above axiom, all above rule that I have said. Now we know that in case of a real number, so vector space has basis. Each vector space has basis, right? That means all the vectors in that basis space are linearly independent and they are exact in number, right? And we know the standard basis for 3 dimension is something like that. And basis is not unique, we know that, right? But we have that standard basis of 3 dimension vector space is basically something like that. That means we can design any vectors of 3 dimension using this 3 vector. Similarly, if P2 is a polynomial of vector space of degree 2, so this is the standard basis for P2, but dimension is 3 because there are 3 elements. Okay. Similarly, if Pn is the n degree polynomial vector space, so this is the standard vector space and dimension is n plus 1. So now here we basically did, here I basically did some examples. So the first example here, you can see that the P3 is said to be a vector space of degree 3. And we said that this Px is equal to ax cube, which also belongs to P3. Okay. And now if we extract this set and we say that whether this Px is a subspace of P3. So what is subspace? Subspace is also a vector space, which also follows this rule, right? So when I'm discussing, if any point, if you find it difficult to understand, you just stop me and ask me question. Okay. So we need to check whether Px is a vector space or not. If Px is a vector space and Px belongs to P3, so Px is a subspace of P3. Okay. So first we have to check that existence of zero vector. So Px is basically ax cube. Now a belongs to real number. So 0 is also a real number. So if we pick a equals to 0, that means Px equals to 0 also there in Px. Px equals 0 also there, and also it follows the additive identity property, right? Now we have to check the vector addition formula, vector addition condition has to be satisfied or not. So if we take any two scalars a1, a2 from this real number, and if we add them, this p1 and p2, we get another polynomial which is a1 plus a2 multiplied with x cube. Now a1 plus a2 is also a real number because a1 a2 individually is a real number. So that means this belongs to this px set, which is ax cube. Now we have to do the scalar multiplication. Now if we take any scalar, sorry, we take any scalar term from real number and multiplied with polynomial, we get this kind of structure where ca is basically belongs to r, right? Because C itself belongs to R, A itself belongs to R, two real number multiplied with each other, then we get a real number. That means this is belongs to the Px set. That means we can say that Px is a subspace of P3. Okay. So this question is okay for you. Now I move to the next question. Okay. So second question that I have asked over here. Let's say consider a subspace of all polynomials of degree n with root at x equals to 2. So the question says that you have to consider all the polynomials of degree n whose root exists at x equals to 2. Okay. And this is the subspace which is defined over here, that u equals to px belongs to pn. Pn is the space of all the polynomials of degree n, and u is the space of all the polynomials of degree n with root x equals to 2. Now we have to find out the basis of u, right? So So what it says, the Pn is a space of all polynomials. So we know that what is the standard basis. So this is basically the standard basis, 1x x square up to x to the power n. Okay. Now it says that Px belongs to U. And also those Px has a root at x equals to 2. So what this line signifies? This means that all the polynomials Px which belongs to U must be divisible by x by 2, right? That means all the polynomial Px must be divisible by x by 2. So we can express Px in this format, that is Px equals to x minus 2 into Qx, where Px is a n degree polynomial because Px also belongs to Pn. Pn is a polynomial of n degree. So Px is a n degree polynomial. This x minus 2 is also polynomial, but the maximum degree is 1. So this is a 1 degree polynomial. and qx, therefore qx should be the n minus 1 degree polynomial. Then we get the n degree polynomial, right? So this means that px belongs to some pn minus 1, whose standard basis is something like that. Okay. Now we can express qx in terms of this standard basis, right? And then if we multiply x minus 2, we get px. So we represent qx in terms of standard basis. Standard basis means all the vectors in this basis are linearly independent. We represent qx in terms of standard basis and then multiplied with x minus 2, we get px. So that means if we multiply this basis vector with x minus 2, we get the basis of u. Okay. So that means this is basically the basis of u. And this is definitely linearly independent because, as I have said, that the standard basis is linearly independent, and then we multiplied standard basis with x minus 2. So obviously they has to be linearly independent, and they are exact in number because the maximum degree at u is x to the power n, and here maximum degree you can see is x to the power n. So this is a basis. Now move to the third question. P3 be the set of polynomials at most degree 3. Consider the following order basis. So P3 is a polynomial of at most degree 3. That means P3 consists of a polynomials degree 3, degree 2, degree 1, degree 0. Right? And it has a ordered basis something like that. This is the ordered basis. Okay. Now says that we have to represent this polynomial fx equals to minus 3 plus 2x cube. We have to represent this polynomial in terms of this basis vector. That means we have to find out the coordinate vector. So since we have already studied vector space and we know that what is the coordinate vectors, so basically we have to find out alpha 1, alpha 2, alpha 3, alpha naught, these values. Okay, so this is basically called coordinate vector. So we represent, so this is the basis vector. So we represent this function using the basis vector, something like that. We have to find out this value, right? Now P3 is a set of polynomials at most degree 3. So it has a standard basis which is 1x, x square, x cubed. We know that this is a standard basis of any polynomial, any polynomial set P3, right? So since this is a standard basis, so we can represent each vector over here using this standard basis. We can represent. So here I'm just writing the coordinate term. I'm just writing over here the coordinate term, that is alpha naught. So this is something like alpha naught 1 plus alpha 1 x plus alpha, sorry, I have to do this. So this is something like alpha naught plus alpha 1 x plus alpha 2 x square plus alpha 3 x cube, right? So now I have to represent 1 plus x using this standard basis. So I have to find out over here what is, or let's say this is alpha, not exactly alpha, this is alpha bar bar. So it's a different thing. Otherwise, we will mix it up with this. So what are the alpha naught bar? So it should be 1, alpha 1 bar should be 1, alpha 2 bar should be 0, alpha 3 bar should be 0. Then we get 1 plus x. Similarly, we get 1 plus x square using 1 0 1 0. Alpha 1 bar, alpha 2 bar, alpha naught bar, alpha 1 bar, alpha 2 bar, alpha 3 bar. Similarly, x minus x square plus 2x in terms of standard basis is 0 1 minus 1 2, and the last vector is 1 minus 1 minus 1 0. So I represent all the vectors in the ordered basis vector in terms of standard basis vector. So just like the previous case, just like this. So I have represent qx in terms of standard basis and then multiplied x minus 2 with the standard basis, we get the basis of u. So I'm doing the same thing over here. And I can also represent the function, I also represent the function minus 3 plus 2x cube using the standard basis using minus 3 0 0 2. Okay. Now I put this alpha naught to alpha 1's value in this equation 2, right? I can put, sorry, I can put all this not alpha not to alpha. I can put all this coordinate vector into equation 2 over here, because I have represented this one with a standard basis, this one with a standard, this one with a standard basis, right? So alpha naught, this alpha 1, so alpha naught multiplied with this, alpha 1 multiplied with this, alpha 2 multiplied with this, and alpha 3 multiplied with this, and this is the equals to this. So we can write it in a matrix vector format. Then we do the Gauss elimination method. How we find out this thing, we know, we have already studied in class 1 or 2. We do the row elimination method. We find out, we do this row echelon form, and from here we get the alpha naught, alpha 2, alpha 1, alpha 2, alpha 3. These are the values. Now if we put these values in equation 1 here, we will get this kind of thing. Now let's see. We put all those values of alpha naught, alpha 1, alpha 2, and alpha 3. We get minus 3 plus 2x cubed. That means these all are the coordinate of this function in terms of the ordered basis vector. So is it clear to you, or do I need to repeat again?
So far clear, sir.
So far clear. Okay. So now move to the next question. So it's basically, it says that C3 is so C3 is a vector space. It is basically a continuous function, a space of continuous function between this interval. So if you see the lecture videos, you can see this is also a vector space. A continuous function space is also a vector space. And say P3 is said to be a polynomials, all the real polynomials. That means all the coefficient of that polynomial is real, not a complex one, of degree 3 or less. Now consider T is a mapping which maps from C03 to P3, and the structure of the T is something like that. Okay, so now we have to check that whether this mapping is a linear transformation or not. Okay, now we know that if V and W are the vectors and C, D are the real numbers, then these two properties has to follow to be a transformation, a linear transformation, right? So we have to check if these two things follows for the same structure or not. So if F and G are belongs to C, then we have to see that T of F plus G should be T of F plus T of G. So we put F plus G into this equation over here. In place of F, we put F plus G, F plus G, F plus G, F plus G, and do the whole things, and we separate F terms together, and we accumulate F terms together and G terms together. We get that F plus T of F plus G is equal to T of F plus T of G. Similarly, the same for the scalar multiplication. We get that T of C into F is basically C into T of F. So that means this is a linear transformation. Now the last question here till now is basically says that L is a mapping which takes the values from polynomials from P3 and maps to the three-dimension real number plane. Okay, it's a linear transformation already said, and define something. Transformation is something defined like that. So L is a transformation, and it takes the polynomials and it gives us this sort of structure. Okay, now find the basis of the null space of L. Basis, or sometimes it says the kernel. Okay, so null space of L is basically all the polynomials, all the what how we find out the null space of a matrix is Ax equals to 0. Like we have to sorry, we have to find out the solution of Ax equals to 0. So this is basically the null space of A. Now here basically L is all the polynomials, which is something this structure with these all terms are 0. Right? That means A minus B plus C is 0, this term is 0, and this term is 0. Then if we take the polynomial and apply this linear transformation L, if we get 0, that means those polynomials are basically exist in the null space of L. So that means this term should be 0. The equation 3, from equation 3 we get B equals to C. If we put this value in equation 1 and 2, we get A equals to 0, D equals to 0. That means the in null space of L, the structure of the polynomial is something like that, bt square plus bt, which is something like b multiplied with t square plus t, right? So what is the basis of the null space? The basis of the null space is something like t plus t square. There is a one vector only in the null space, t plus t square. Okay, so this is so far. Now I just shortly discuss about the inner product space and give one or two example, and then I'll wrap it up. Okay, so inner product space is something like it has following properties. Just a minute. So basically, a real or complex vector space V is said to be an inner product space if the first thing VW belongs to V, then some lambda V plus mu W and X, X, V and W belongs to this capital V, then the inner product, this sign, this angle sign is called bracket. Okay, so this is something like inner product lambda into V plus mu W into W and X. Something, the second thing is VW. If V and W both are real, then this should happen for real case. And if V and W are complex conjugate, then this should happen. And V, inner product of V always greater than or equals to 0, or rather if say it is greater than 0 for V not equals to 0, and this is equals to 0 for V equals to 0. So this is the inner product. So this is basically a symbol. So inner product is basically, so VW, this is basically dot product V transpose W. Okay, this is basically something like that. Now take an one example from here. Okay. So let S equals to is V1, V2 up to Vk be an orthogonal set. So S is a orthogonal set which consists of V1 to Vk. So where Vj is not equals to 0, so then S is, sorry, then show that S is linearly independent. Okay, So the first thing you can see that since so consider, so we have to show that S is linearly independent. That means for linear independency, what we have to show that alpha 1 v1 plus alpha 2 v2 up to plus alpha n alpha k vk, this is equals to 0 if and only if all those alpha i's are 0. If this is satisfied, this property is satisfied, then we say that v1 to vk are linearly independent with each other. If any of the alpha i's is non-zero, then we can't say they are all linearly independent, right? So now we consider same thing like alpha 1 v1 plus alpha 2 v2 plus up to alpha k vk equals to 0. Okay. Now we took the inner product both side with a v1. So this is took the inner product both side with v1. So what would happen? Alpha 1 v1 inner product with v1. Sorry. So alpha 1 v1 plus alpha 2 v2 up to plus alpha k vk took an inner product with v1, and then here I'm going to take an inner product of 0 with v1, right? Now using the property of inner product space, first property, we can write it in this format. Using this first property, we can write it in this format, right? So what we can write? We can write alpha 1 v1 with inner product v1 plus alpha 2 v2 with v1 plus up to alpha k vk with v1. Okay, and this term is 0 because 0 with v1 is equal to 0. Now what it says? It says that v1, the question says that v1 to vk all are v1 to vk all are orthogonal, right? So since orthogonal, the property of orthogonality is vi transpose vj equals to 0 if I not equals to j, and they are equals to some value if they are non they are I equals to j. So orthogonal property what says? Sorry. So vi transpose vj equals to 0 if I not equals to j and equals to some value, let's say some constant p if I equals to j. So that means all these terms are 0, right? So what we get alpha 1 v1 inner product with v1 equals to 0. So this is something that we get, right? Now we have also mentioned over here that vj is not equals to 0. That means none of the v are 0. So from the inner product property, v inner product with v equals to 0 if and only if v equals to 0. Otherwise, this gives a positive answer. Okay, greater than 0. So this term is basically non-zero term. So non-zero term multiplied with the constant will give a zero term. It only possible when alpha 1 is 0, right? So this is only possible if alpha 1 equals to 0. Now you can do the same thing, same again and again, same procedure for multiply this whole
multiply this equation, sorry, inner product is equation with V2, you get alpha 2 equals to 0. Similarly, inner product with Vk, you get alpha k equals to 0. So similarly, you see that all the alpha i's are 0. So that means we can prove over here that if the vectors are orthogonal to each other, then they are linearly independent. Okay. So I hope this is clear to you. So now here I have stopped my video, stopped my discussion. Now the extra session, there will be an extra session. You will get the announcement. There will be extra session, which will be I mean, obviously we will get the announcement for that. So on extra session, if you have any kind of queries, you can ask. You can